All right, let's look at section 3.6, the derivative as a rate of change. So we've already talked about this. This was kind of like, we talked about this already. So what's kind of nice is that we come back to this section, we kind of reinforce the idea, and then we talk about a couple different applications. All right? We revisit all the velocity derivative stuff, but then we also talk about marginals. All right? So it's a different application. So let's just kind of get started here. This is one of the things on your take home. But you know, like if you have a function, f of a, this is the output at x equals a. F prime of a was the what? It was the slope, and then more generally it was the what? Rate of change. So rate of change of outputs to inputs. Okay? So we got capital T of little t represents the temperature in degrees Fahrenheit, little t hours after 10 a.m. Suppose that 45 degrees at noon, 48 degrees at 2 p.m. It asks us to approximate t prime of 4. So t prime at 4 would be the slope of the curve at 4. It would be the rate of change of the temperature at 4. We're asked to approximate it because we're not given any formula for the temperature. We're just given 2 temperature points. Follow? So let's look at each of these here. 45 degrees at noon. So T of what equals what? Well, capital T is the temperature. Little t is the time, but it's the time after what? 10 a.m. So noon is how long after 10 a.m.? 2 hours. So that's that information. We're told it's 48 degrees at 2 p.m. So what equation do I have from that? T of 4 is 48. Are we all cool with that? Now, T prime at 4, we can think of that as the slope at 4. We can think of that as the rate of change of temperature at 4. This would be equal to the limit as x approaches 4. Well, I guess of t, say t approaches 4. Of t of t minus t of 4 over t minus 4. So that's the limit definition of derivative that we had last week. But once again, we're not given a formula for the temperature. We're just given this other point. So remember what this, the tangent line slope was a limit of the secant line slopes. The instantaneous rate of change was a limit of the average rate of change. So we'll just put this really rough approximation here, because the only other point I have is what? 2. So it's going to be roughly t of 2 minus t of 4 over 2 minus 4. So do you see why it's an approximation here, folks? So you can think of this as we're looking at a slope of a secant line approximating the slope of the tangent line, an average rate of change, approximately instantaneous rate of change. So let's work through this here. T of 2 was 45. T of 4 was 48 over minus 2. So when the dust settles, what do I get out of this? 3 over 2 or 1.5 if you want to write it as a decimal. So that's the numerical value approximated once again using a secant slope. So secant to tangent. So that's kind of the big the big thing we did last week. So T prime at 4, roughly 1.5. Use T prime at 4 to approximate the temperature at 5 p.m. Okay? So once again, the derivative is a slope, it's a rate of change. So when we say T prime at 4 is roughly 1.5, that should tell us about the rate of change of temperature. So that 1.5 really, if I think about the units, what would the units be? If it's a rate of change, it would be the rate of change of what to what? Yeah, so this would be degrees Fahrenheit per hour. Does that make sense or not? And the fact that we have a positive here tells us what about the temperature? Yeah, it's getting bigger. It's warming up. Okay? So at 2 p.m., the temp is warming up at 1.5 degrees Fahrenheit per hour. So let's look at 5 p.m. Whoops. If we want to use this information to approximate what's going on at 5 p.m., how would we do it? At 2 p.m. to 5 p.m., that's how many hours? 3 hours. According to our derivative, the temperature is doing what? Increasing at 1.5 degrees per hour. So the temp at 5 p.m., well, we're going to start at 2 p.m. What's the temperature at 2 p.m.? 48 degrees Fahrenheit, and then I'm going to add how much to it? I'm looking at how many hours later? So then I would have the 1.5 degrees Fahrenheit per hour times 3 hours. All right, so this would be T at 4 plus T prime at 4 times 3. That would be 48 degrees Fahrenheit plus 4.5 degrees Fahrenheit. Gives me a grand total of what? 52.5. Make sense or not, folks? Okay. So derivatives are slopes, but more generally they're rates of change. You use them as you would any other rate of change. Make sense? All right, so this was, once again, we're just reinforcing stuff we talked about last week. Let's look at example 2 there. We got a graph, models the population of black bears in a certain county, P of T years after they were introduced in the year 2000. So here we go. So this is the year 2000 is here, and it goes way into the future there. So I'm going to grab a handout so I can look at it. Questions. Approximate the limit as t goes to infinity of P of T. What does your answer mean in terms of the black bear population? So here's the t-axis down here. Here's t going off to infinity. Where does that curve look like it's going to level off at? Leveling off at what? Yeah, 400. Okay. Looks to be 400. Is everyone cool with that? Graphically, that's called a what? Yep, that's your horizontal asymptote. You follow? So that means that as time goes by, the black bear population is going to start to do what? It's going to level off at 400. Does that make sense? Sometimes that's called the carrying capacity of the environment. Right? The environment will only support that many black bears because of resources. You with me or not? Okay. Which is greater, P prime or of 100 or P prime of 300? What does this mean in terms of black bear population? Okay. They're looking at P prime of 100 and P prime at 300. So here we go. So here's the 100 down here. These are T values. I go up, and once again, when I'm looking at P prime, what am I looking at geometrically there? Slope. So go up at 100, there it is, and I just sort of imagine the tangent line there. And then I go up to 300. I imagine the tangent line there, and which is bigger? P prime at 100, right? Geometrically, it's because the slope is what? It's steeper. It's more positive than it is. So what does that mean about the growth rate of black bears? There are more black bears when T is 300 than there is at 100, but their slopes, that means that the black bear population is starting to do what? Starting to level off. You follow? It's not growing as quickly. Is P double prime at 200 positive or negative? What does that mean? So now we're looking at P double prime. And remember, the second derivative is the derivative of the what? First derivative. So we're looking at, so it's the rate of change of the what? Rate of change. So let's kind of go into here. And so what we need to do is we need to think about what's going on with these slopes. You follow? Because I'm looking at the rate of change of the slopes. So as we mentioned, those slopes are getting what? They're getting smaller, which means the derivative of those slopes should be what kind of number? Are the slopes getting bigger or smaller? Smaller, they're decreasing, so that rate of change would be what kind of number? Negative. Does that make sense or not? Because they're getting smaller. Which means that the rate of change, the growth rate of the black bear population is getting smaller, which means because it's tapering off. Does that make sense or not? So we talked about a second derivative in terms of like acceleration. But here's a second derivative in terms of sort of a life science kind of example. We'll talk more about second derivatives next week. Any questions on example 2 there? You see how we're interpreting these rates of change? If a rate of change is positive, it means that quantity is getting bigger. If a rate of change is negative, that means that quantity is getting small. All right, one-dimensional motion. I believe this is what, the third or fourth time we've talked about this. So once again, here it is. I think this is the third time we've seen this. It may be the fourth, I don't know. Maybe, because it was on the take-home, right? You had one of these on the take-home? So maybe that's why it's the fourth time. Suppose an object travels along the x-axis according to this formula. So let's check that out. S of t is 6t squared minus t cubed for t bigger than or equal to 0. Bless you. Find expressions for the velocity and the acceleration. So here we go. So velocity, remember, is the what of position? Derivative. So I need to take the derivative of 6t squared minus t cubed. And hopefully you've practiced this enough. This is going to be old hat. What's the derivative of 6t squared? The 2 comes down, multiplies the 6, gives you 12. T squared drops the power from t squared to t. Minus, what's the derivative of t cubed? There it is. Now how do I get to acceleration then? Acceleration is the what? Second derivative of position, which means it's the first derivative of velocity. Whoops. All right, a of t is, what's the derivative of 12t? Minus, what's the derivative of 3t squared? 6t. So here are the expressions, velocity and acceleration. Okay. When t equals 5, where is the object? Which direction is it moving? Is it speeding up or slowing down? Okay. So once again, a nice little review here of what all of these different things teach us. So I'm going to just recopy these, just so we have them all on the same page. So we're looking at t equals 5. So if I want to know where the thing is, which of those three functions do I plug that into? What's the where function here? Yeah, position. So s of 5 equals 6 times 5 squared minus 5 cubed. And, you know, it's early on a Monday. Let's factor that 5 squared out, and then we'll get 25. Yeah, that's an easier way to do it. So remember, this object is traveling along which axis? It's on the x-axis. So when t equals 5, we're at what? 25. That's when t is 5. When t is 5, the object is at x equals 25. What's on the agenda for chemistry today? What are you working on? What's that? Ooh, kinetics. Okay. Now, it's asking which direction is it moving. So which of those functions is going to help us figure out what direction it's moving? Velocity. Okay. If velocity is positive, since I'm moving on the x-axis, if the velocity is positive, the object would be moving to the what? Right. If it's negative, it'd be moving to the left. So let's figure that out. Let's plug in v of 5. 12 times 5 minus 3 times 5 squared. So that's 60 minus 45. No, 60 minus 75, which is what? Negative 15. Since it's negative, that means it's moving to the what? Left. So here's where the object is. You follow? And now I know that it's moving that way. You with me or not? Is the object speeding up or slowing down? So I know it's moving to the left. Is it speeding up or slowing down? For me to figure that out, I have to figure out the rate of change of velocity, which is what? Acceleration. So I'm going to look at the acceleration now. So I got 12 minus 30, which is what? So this means that it's accelerating to the left. You follow? So if I'm going to the left and I'm accelerating to the left, that means that we're doing what? Is it speeding up or slowing down? Speeding up. Does that make sense? So once again, if velocity and acceleration are either both positive or both negative, it means that the object is speeding up. Because acceleration is making it go in the same direction. The acceleration is in the same direction as the motion. Right? So it's speeding up. Solve and interpret v of t equals 0. So let's, this is a two-parter, solve and interpret. So the solve part is the algebra part. So I've got to take my v of t. I've got to set that equal to 0. And how can we go about solving that? What can I factor out of both terms here? A 3t, and what am I left with then? 4 minus t. So we've got two real numbers multiplied together to give me 0. That means one or the other, or both are 0. So what do I get? T is 0 or t is 4. Okay? So that's the solve part. That's the solve part. We found when v of t is 0. What's the interpret on this? What does it mean if the velocity is 0? Yeah, it has stopped. You follow? If the velocity is 0, that's the speed is 0. So it's momentarily still. So we could say the object has stopped. That's a perfectly good interpretation of that. So anytime you see a take-home or a test or something, something and interpret. The interpret means that, what does this tell us about the journey of this object? Now it asks us to make a sign diagram for the v of t. And we're going to be using sign diagrams extensively next week. Okay? Now, what a sign diagram is, S-I-G-N, sign diagram. It tells us where a function is positive, negative, 0, or undefined, depending on how pathological the function is. So that's why it's called the sign. I care about plus, minus, 0, and then, if it messes up. So if I look at my v of t, it's 12t minus 3t squared. And here's how I like to think about a sign diagram. I'm just going to draw the number line here. And I'm going to put the t's down here, the inputs, and then the v of t's up here. So down here are going to be the t values I've got. And then above it, the v of t, these are going to be the sign values. Now the first step in making a sign diagram is always to figure out where the function is undefined or 0. So looking at our v of t, it's a polynomial. There's no dividing by 0 that can happen. Everything's fine. V of t is 0, we just found, at 0 and 4. So here's t equals 0, and t equals 4. Moreover, if I look at the original problem, so look at the original problem here, the only t's we care about are t's that are what? Bigger than or equal to 0. So in fact, I guess technically things are undefined back there. We don't care what's happening on that part of the number line. You follow? Okay. So what I'm going to do above the numbers is I'm going to record the sign. So here the sign is 0 because that's where the v of t is 0. You follow? Now, once you've taken care of where the function's undefined, you've taken care of the places where the function won't be continuous. You follow? So this function is going to be continuous from 0 on out. And what do we know about continuous functions? Graphically, if you start a continuous function, it means that when you graph it, you never have to pick up your pen or pencil. Follow? Conceptually, continuous function means close inputs give you close outputs. The intermediate value theorem says intermediate function values come from intermediate input values. Follow? That's all the stuff that continuity has to offer. So let me ask you this. I'm trying to figure out the sign of this function on these intervals. Let me pick a value between 0 and 4. What's your favorite number between 0 and 4? 2. Okay? Let me figure out what the sign of the velocity is at 2. When I plug 2 into the velocity, I don't care the actual retail value. Is it going to end up being a positive or negative? It'll be a positive. Okay. Now, what if I picked 1 or 2.5 or 3.999? They would all be positive. Why? Because if they did switch to negative, they would have to go through a 0 first because of the intermediate value theorem. Follow or not? And now we already did t equals 5 here. And we know that t equals 5 is negative. So you remember making these things back in algebra to help you solve like inequalities? Okay. So we're going to be doing a lot of sign diagram work next week. But basically what this means in terms of the life of this object is, once again, I'm moving along the x-axis here. When t is 0, I get 0. Let's see. When s is 4, let's see where that is. What was my s at t? Once again, it's early, so let's factor this out. 32. So the thing starts here. It starts at x equals 0 when t equals 0. And then it moves over to x equals 32 when t equals 4. And during that time, it's moving to the right. As we would expect, it's moving to the right. At t equals 4, it stops, and then it starts to do what? Move to the left. So when it stops, that's giving it time to stop and then do what? Turn around, and then it's going to be heading that way forever and ever. You with me or not? So it moves to the right for the first 4 seconds until it gets to 32. It stops, turns around, and it's just going to head the other way. You with me or not, folks? All right, example 4 is a video. Once again, it's really helpful for you to connect the analysis, the algebra, with the geometry here, with the graphs. So example 4 will help you with that. Example 5 is yet another example. In this case, the motion is along the positive y-axis, so it's vertical. We've got a slightly more complicated function, but we're asking the same kinds of questions. So you have practice on that. Okay, the last half hour of class or so I want to spend talking about some business applications. So a lot of times, especially in the algebra class, they like to do these business problems because it's something most people can relate to. So you may recall the concept of cost. The cost to produce X items is denoted by capital C of X. The average cost to produce X items is often called, with a bar over it, C bar of X. Is C of X divided by X. So, for example, if it costs $60 to make 5 items, C bar of 5 would be the total cost, $60. Divided by 5 items, so that would be $12 per item. Make sense or not? That's average cost. The price demand function, little p of x, gives the price per item to charge in order to sell x items. So if you had like p of 2 equals 5, the 2 that's going in, that's the number of items you want to sell. what comes out is the price per item. So this scenario, if you want to sell 2 items, you would charge $5 per item. Okay, so it's price demand because it connects the amount of money you're paying, the P of X, that's your price, with the X, that's the amount of things you're going to sell. The revenue, that's how much money you bring in. That's the money collected by selling X items. So what do? We take the number of items you sell, X, and we multiply it by the price, P of X. Does that make sense or not? So if you sell 2 items at $5 an item, your revenue would be 2 times 5 or $10. Does that make sense? And then the profit, that's your bottom line. Capital P of X denotes that. That's the money you're going to earn after you pay your costs. So that's your revenue minus your costs. Does that make sense or not? Have you seen these sorts of concepts before? So example 6, hopefully is a trip down memory lane. You're making these t-shirts here. And it's basically a review of the algebra. So read through it, make sure it makes sense to you. But we're going to focus on business applications with calculus. And the business application is going to talk about our marginals. So a marginal is looking ahead to the next item. So a marginal cost is looking at the cost to make one more item. A marginal revenue is how much extra money you'll bring in if you sell one more item. Marginal profit is the profit you're going to make if you make and sell one more item. You follow? So that's what marginal is. You're looking at the next one. You follow? So the way this works is, once again, like let's take the cost function. If you take the derivative of the cost function, the definition is, that's our definition, you follow? And so once again, we can approximate this if I take the limit off. For h small. And if you're just measuring things discretely, like you're going one item to the next, the smallest h can be would be h equals 1. So c prime of x is roughly equal to c of x plus 1 minus c of x all over 1. And so this is the concept of marginal. So this is the dollars per one item. So I'm going to take that one item and multiply it over there. And so basically what this says is the additional money to make one more item is approximately equal to the derivative times one item. Does that make sense? So the derivative would be dollars per item, and I'm multiplying it by one item. That's going to be the approximate additional cost. And you can do that with revenue, and you can do that with profit. So here's sort of the summary there. Okay. So we can define then the marginals this way. The marginal cost, MC of x, is the derivative c prime of x times one item. Now once again, number-wise, when you multiply a number by 1, it doesn't change the number. 1 is the multiplicative identity. But I put one item there to make you remember that marginal cost is going to be a dollar amount. You follow? Not a dollar per item. Marginal revenue, same thing. Marginal profit, same thing. All right, so we've got this economic scenario above. Once again, you can review this example in the privacy of your own home. But we're gonna use this and talk about marginal and averages. So here's the cost in dollars to make X t-shirts. So C of X is 2X plus 26, for X bigger than or equal to 0. X is the number of t-shirts you make. C of X is your cost measured in dollars. So the first thing we want to talk about in this scenario is find MC of 7 and compare this to C bar of 7. So MC of 7, or MC of X rather, is the derivative of X times one item. So what's the derivative here of C of X? 2. And what's 2 times 1? Oops. So that's MC of X. That's the marginal cost, is 2. So MC of 7 would be 2. And once again, what does this represent? This is the approximate additional cost it would take to make the next item. You follow? So if we're making 7 t-shirts, the next item would be the what t-shirt? 8th t-shirt. So the approximate additional cost or we could write it this way. It'll cost approximately $2 to make, well, it'll cost approximately additional $2 to make the 8th t-shirt. So marginal, you're looking at the next one. So it's going to be an additional $2 to make the 8th t-shirt. C prime of 7, or C bar of 7, that's your total cost to make 7 shirts divided by 7 shirts. That works out to be 5.71. So the average cost per shirt is $5.17. Now, so looking ahead, you're making 7 t-shirts. The 8th t-shirt is going to cost you an extra $2. The average cost per shirt is a little over $5. So if I make more shirts, what should happen with that average cost? If the current average cost is 5 and change, but the cost to make the next one's only 2, then what should happen with the average cost if I go ahead and make the next one? It should decrease, you follow? And that's a theorem that actually you're going to be proving in the next take-home. Find and interpret the marginal revenue at 7. Okay? So the marginal revenue, once again, that's the derivative of the revenue times one item. So let's look. Once again, we're going to go back to the previous example here and pick up the revenue function. Was minus 2x squared plus 30x. And so we take the derivative of that. What happens to the exponent 2? Comes down, going to multiply, give me a what? Negative 4x. What's the derivative of 30x? 30. Okay. And once again, that times 1 there doesn't affect the formula, but it reminds us that the interpretation is no longer a rate of change. It's looking at the next one. So if I look at MR of 7, it's minus 4 times 7 plus 30. That's also what? 2. But what does this 2 mean? So marginal revenue is looking at selling the next item. So here we're selling 7 t-shirts. We're looking at what would happen if I sold what? Another t-shirt, right? The 8th t-shirt. So selling the 8th t-shirt should generate an additional $2 in revenue. Right? So the next t-shirt, we're selling 7, the next one would be 8. So selling the 8th t-shirt should generate an additional $2. Make sense or not? Okay. Now, we just showed that the marginal cost at 7 was $2. So to make the 8th t-shirt is going to cost us about $2. When we sell the 8th t-shirt, we're going to generate an extra what? $2. So what would be the marginal profit then in that scenario? The marginal profit at 7, that's how much we're going to make after cost. So if we make and sell the next t-shirt, that's the marginal revenue at 7 minus the marginal cost at 7. Does that make sense? So 2 minus 2, which is what? 0. So even though we're going to make more money, we're going to just lose that at the cost. So is it worth making the extra t-shirt? We're going to lose it. And in fact, if we go beyond that, what could happen? Yeah, the marginal cost could outstrip the marginal revenue, and we don't want that because that means that profits would go down. Right? So as I mentioned when we talked about derivatives, the very first day of derivatives, we used it to approximate square roots or something. Right? On the test, you approximated a cube root, hopefully, successfully with a derivative. But also they can be used in these other settings like businesses to kind of predict changes. Right? So has anyone taken like an economics class? They talk about marginals. They usually in those classes, if it's not calculus based, everything's linear. So their marginals are literally their slopes. But this is you can have marginals of anything like that. All right, and then here's the homework there. Okay. So what did we learn today? We've got derivative formulas now for the trig functions. On the surface, there's 6 formulas you should know, but really there's 3 plus a pattern. You follow? And then what did we do? We just came back and spent more time talking about reinforcing derivatives as rates of change. Okay?